Hi, I'm John Cox, and this is my lab for magnetic field of a bar magnet. Introduction. Here's some equations I used with like Biot-Savart law, things like that, and dipoles, magnetic dipoles. I wanted to explore how the magnitude of magnetic field changes as a function of distance, evaluate measured data against theoretical predictions derived from the Biot-Savart law with on-axis and off-axis. I want to develop techniques for visualizing and interpreting magnetic field behavior. Key results are field strength grows as the magnometer approaches the magnetic dipole of many amps and an N value. Assumptions and initial conditions. Coordinate system assumptions, x-axis directed out of the screen plane, y-axis aligned with the vertical height of the phone, x-axis aligned with the horizontal width of the phone, field magnitude assumed proportional of a constant times power of distance r. Initial conditions, phone orientation. Phone initially rotated to identify magnetic north and isolate Earth's background field. System magnometer sensor phone plus bar magnet. Surroundings Earth ambient magnetic field treated as a background to be subtracted. Experimental process. Find the magnetic north. Rotated the phone with using magnometer at until the x component read near zero, establishing the north orientation. Align the apparatus. Position the meter stick east to west, perpendicular to magnetic north with the bar magnet fixed at one end. Look at the sensor. Use charge tape to pinpoint the magnometer's exact position on the phone, where X and Y field components peaked. Record on-axis distances. Measure distances producing X component magnitudes. Measured off-axis distance. Determined that the perpendicular distance at which the total field magnitude equaled 100. Spreadsheet below summarizes all measured distances, raw field components, Earth field corrections, and the log linearized values used to extract the power law fit. The embedded plot shows ln bx versus ln r, getting a best fit slope of that. Applications and key results. Step 1, fit the log linear model. Taking the natural log of the power law model linearizes the relationship, allowing a simple linear regression to extract both the exponent and the prefactor. Extract the n value, the slope of the best fit line. It's consistent with theoretical dipole prediction from Biot-Savart law. Step 3, determine the magnetic dipole moment and the y-intercept. Setting k equal on the on-axis dipole formula yields a magnetic dipole moment of 3.571. Here's my glow script computation model. The following code snippets implement magnetic dipole simulation in glow script v Python, computing the field vector at arbitrary positions along the dipole equation. Here's my glow script visual model and comparison. X and Y components align closely between experiment and simulation. Non-zero Z component is measured. Data is attributed to Earth's residual field and minor sensor misalignment. Computation model excludes this background. Some what ifs are, if I hadn't compensated for magnetic north, it would superimpose the background field onto the magnetic field. The X component readings would no longer isolate the magnet alone, introducing systemic error into every distance measurement, integrating the accuracy of both the n value and the dipole moment calculation. What if two identical magnets were used end to end? Sticking two identical magnets end to end effectively doubles the dipole moment while preserving the same field geometry. Explosive error, measurement uncertainty, external magnitude interference, physical disturbances. Thank you. Bye bye.